Visible?
Yes, sir.
Yes, sir.
Yes, sir. Fine. So today we will discuss about this topic. I mean, we'll start this topic that is on concept learning. And let us start with an example. So before that, let me mention about the references that you need to go through for this topic. It is the machine learning book by Tom Michel. So we'll be covering chapter 2 mostly, and then some of the part of chapter 7, where some foundations of computational learning theories will be also covered in this particular topic, under this topic. And also there is a chapter in Alpedein's book, that is also chapter 2. It is called supervised learning, but you will find particularly the concepts related to the theory of computational learning. Those are discussed there under that scheme. It is not exactly concept learning, but that part is there. That is why it is mentioned. So let us consider an example by which we will understand what is meant by this concept learning. You can see that there are few terms which are highlighted by those small blue boxes, like sky condition, humidity, temperature, wind, water, forecast. Now, they are considered as some attributes for a day, and they takes values, and those values are shown. Sky condition could be rainy or cloudy or sunny. So we assume that only one of these values will be true for any of this attribute or variable, in what way you can consider. Humidity could be high or normal. Temperature could be warm or cold for describing a day. So wind strong or wind weak. Forecast could be the same for the next day, or it may change for the next day. Water could be warm or cool. I found it is a bit funny that this is also an attribute for the day, but it is there. But actually, the context, let us understand the context also, that for which this description is there. So what we need to find out that whether a person enjoys sports or not. Enjoying means either the person participates in an event of sports, or can watch sports by going to the stadium. That means it's an outdoor activity we are considering. Of course, these are all outdoor features, as you see, that whether the person comes out from his or her residence to participate in the outdoor. So the question would be answered in the form of yes or no. As you see, that's a kind of binary answer. We can express, in fact, these things. We all know that a Boolean variable can capture well, particularly this concept. So these are the concepts, and particularly the relationships between them. These attributes are mostly the, I should say, the concepts. So what is the learning task here? In the learning task, we are trying to find out whether, as I mentioned, that given those attributes of a day, whether a person comes out to enjoy sports. So suppose this is what we would like to find out, and for that we need to form certain hypotheses, or express it in the form of a relation, so that if you apply that hypothesis or relation, then you can predict whether the answer is yes or no for that particular task of enjoy sports, or that concept of enjoy sports, what I mentioned. So first thing, as I discussed also in the previous class, that in a machine learning task or in a learning task in general, we need to make it a bit more precise further. So how to represent this answer, how to represent this particular relation, in the sense, this hypothesis. So that is very important. So the form is very important, and then only then your problem becomes more specific to discover a form given certain options. Or rather, I should say, we we will be more technical. Instead of calling it a form, we say it's an hypothesis. So discover a hypothesis from a space of hypothesis. So we need to define this representation, which will define the space also. So in this case, in this example, we will consider that this is represented in the form of a Boolean function on the attributes of the day. So please note that this is not the only form for concept learning. This is one form, as I mentioned, that is a kind of assumption on the form that you have to do always in a learning task. And then you proceed for discovering that form or deriving that from the data. So that is also another part. That means if I give you the data uh, which captures these particular facts, that what are the days, what are the attributes of those days, and what happened on those days. That means whether a person has enjoyed sports, whether a person has come out to enjoy sports. It's a kind of, you can see that one application would be that you have an event and you would like to estimate the number of spectators that you are expecting. So, so maybe, in that context, this type of learning would be more relevant. So here, this is your learning task. That means you have to find the right hypothesis or function from historical data, and which we call as training examples. That means those data, those are given as the training examples. So let us take this set of examples. So what has been given to you? It's a toy problem which we will be discussing. So we will consider only a few training examples. And suppose this is the only set of training examples that is with you, and you would like to learn the corresponding hypothesis regarding this enjoy sports. So you can see that there are certain facts are shown here in each row of this table, and in the columns the name of those attributes are also given. So the sky could be sunny, and when the sky is sunny, if this is a particular training example, when temperature is warm, humidity is normal, wind strong, water warm, forecast the same, then you can see that this is the first row that we can say, okay, yes, this is the conditions for enjoying sport. I mean, that is what is given from the fact, and let us assume there is no contradiction in the data. That means, no, for the same set of attribute, no, you do not have its negation also. Then, of course, you understand that you cannot learn. I mean, that's a contradiction. And then naturally, the data has some fault, some noise. And so that is one kind of error. Though even there may not be a contradiction, but still in the recording there could be an error. That is another aspect. So we will not consider any error, any kind of error in the data in this particular problem. So we have only 4 such cases, and 3 cases are yes, and 1 case there is no. So I can say, suppose let me consider represent that C is a function. C is a function of these attributes, and which outputs a Boolean value, either 1 or 0. So, so I write it in the form of a mathematical form, like C is a function of sky, temp, humid, wind, water, forecast, and it outputs a value of enjoy sport. Again, that's the space, so you have either 1 or 0. So typically the values are shown for the first row. Similarly, this is another sets of tuples or a set of attributes, and from there you get the functional value. Whereas when the value is no, then for those values of attributes you get the functional value as 0. So what you would like to learn, you would like to learn this function. So you have been given only few cases, as you can see. So can you tell me that what should be the total number of input vectors if I consider they are vectors, or yeah, I mean they are as a vector in the space. of sky, temp, humid, wind. So what is that dimension? It's a 6-dimensional space. And in the previous slide itself, I have given you the set of values. So these are the set of values. Can you tell me that what should be the number of total input vectors? Input space. What is the size of the input space in this case? Anyone?
6.
6.
6 is the dimension. 6 is the
96.
dimension. Yeah, it should be 96. It just multiplies. So it is basically 3 into 2 into 2 into 2 into 2 into 2. Is it clear? Okay. So that makes 96 because you are taking one of those values in every attribute, and that is how it is coming. So that is a input side, and you have a typical functions. Only few values are shown here. So actually, learning is that given the partial description of the function, you are trying to find out what should be its full form, right? What should be its full representation, and we call that function as a target function. And you have these negative and positive learning examples, and we would like to learn the target concept. See, so this is the term concept. So I hope you understand now that the context by which this term is used. So can you tell me that how many target concepts could be there? How many target concepts? You have 96 input samples, as you can see. For C, the input size, input domain is 96. So how many target concepts?
2 to the power 96.
2 power 96.
Very good. 2 to the power 96. It's quite a bit large space, as you can see. So you have to learn one of these concepts, right? That is what is meant, but that's not all. That's not all in the sense that there could be so you can see only that you have been given this training data. So I can say how many possibilities could be there. So given these training samples, how many possibilities could be there? So that is another good question, isn't it? So as we can see, say in a brute force way, I can probably say, but I need to examine it carefully. Suppose you have 4 samples, target samples, where I think that is fine. So from 96, you exclude these 4 which are fixed. So you have another 92. You have another 92 samples. So you have 2 to the power 92 concepts, 2 to the power 92 possible target concepts are there. I hope you understand that it's a huge task to say that which one is true. You can choose any one of them, and this target this particular example should be satisfied because we have already fixed them, right? But of course, that is not the that is not you want, and that should be very trivial learning in that sense that you select and you just satisfy these samples. So you can put more constraints on that. One of the constraints could be that suppose you would like to express them in a Boolean form, Boolean expression. Suppose all these literals say, I would like to say sky equal to sunny is a Boolean literal. It's not sky, it is sky equal to sunny. It is temp equal worms. It's a Boolean literal. It could be false or true. These are the true values. So suppose I consider in that kind of form, then what is the minimal representation? What is the minimal representation of that function which will give me this target concept? So that may be, I should say, a further refinement of this problem, and you are going to learn it, and that may look more practical from the point of view of learning problem. So it is just not formulation of learning problem is very important. As you can see that I give you training examples, and in general I can say, please give me a system which will predict whether a person enjoys sports or not, right? That's the meta level description, but you need to further refine it and try to make it more mathematical representation of the problem and then solve it. So we'll go through these exercises more and more in different examples, in different approaches also. So just to summarize, that C is the target concept, and as you can see that I would like to express this target concept as Boolean function. So in a very trivial descriptions could be, it's a conjunction of all such truth values, and that could be one description. Conjunctions of all such not conjunction, disjunctions of all such truth values. That could be disjunctions of conjunction of all these truth values. It's a kind of an expression, which means I can write it, I can say that, okay, sky in one conjunctive form, not CNF form or conjunctive normal form. I hope you understand. That means that every literal are ANDed. You are using only AND operations while expressing a particular expression. So which means sky equals sunny and temp equals warm and humid equals normal and wind equals strong and water equals warm and forecast equals same. So this is one conjunctive normal form. And when this is true, then of course, as you can see, it satisfies this training example. So we say that this is one representation, or then consider the next conjunctive form, CNF form. Or you consider the next positive example. So exclude all the negative examples. So this could be one trivial way of expressing a target concept. But as you understand, that is not our objective. We would like to make it also minimal representations. So we'll go through this part. So this is what concept learning, as I was explaining with examples, that you need to derive a Boolean function from training examples, and you have to find H such that H equals C. It is a true target function. So that H should represent true target functions. Of course, you do not know what is that true target function. That is the question. Only partial description of it is available to you. However, you have to generate hypothesis, and as I mentioned, that you apply certain constraints on the form of those target concepts and target functions, and from there, your hypothesis space you are trying to restrict also. If you keep it open for the whole hypothesis space, complete space, there would be also several other limitations of discovering the fact. So you are trying to apply more constraint on the hypothesis space, so that from there you are trying to select your assumptions should be driven by certain practical considerations. So those are also there in a concept learning, and we call them, those are inductive bias. We'll come to those concepts later on also. We'll describe them. So you have to generate those hypotheses from those constraints. So as I mentioned, there are many hypothetical Boolean functions, and one of the kind of constraint could be that these hypotheses are only as conjunctions of constraints. That means only in a single CNF form. There is no disjunctions of CNFs. There is no or in between those CNFs. Only one single CNF. It looks little very constant, but actually not, because I will be explaining also that how to generalize that representation also. There are some other notations we'll be using, just not a single literal. A literal could express a number of Boolean conditions. So we'll be considering that also. So let us understand first, and let us consider that. So each constraint is a Boolean constraint or attribute values. Now there are three forms. So far I have only considered only one form. That means sky equals sunny. That is one form. Sky equals rainy, and I think sky equals cloudy. These are the three things we consider. So one of them could be there. So that those are the three forms. So this is one kind of form. But no, I can generalize it. In this case, the example was taken from water. So a very specific value can be assigned, and that forms a literal. Or I can say any value should satisfy this condition. So it is something like I am including also a conditions like warm or I think it is warm or cool. So warm or cool, both are there. So water equals warm or water equals cool. That forms a clause. Now the constraint is that I consider only one kind of disjunctions are there. That means it is disjunctions of all possible cases. That is one form, and the other case is that it may not be there also. No value allowed. So that means it is a negation conditions. That means which means in your case that for that attributes, if that attribute exists in your space, actually that the whole target concept will be always false. Now this is a very I should say very hard constraint. That means it is null, and either you should exclude that attribute space to express the Boolean function, but if you include it, which means that your target functions will be always null. So this is a but these values are also there. I mean, as in a target functions in the space, you can always consider also that none of them are true. None of them are true. So I mean, which means that no, you are not really favoring that attribute in a way. So these are the, you see that these are the three forms. So now you can see that no, what should be the number of possible Boolean literals, say of water. Suppose water has two values only, acceptable values, warm or cool. So how many literals would be there? Boolean literals would be there?
Four.
Four. Yeah. For sky, if you remember, there are three conditions where there it should be 5. Yes, that's right. So if I consider that, now you can see that no, how many functional forms could be there. Now the hypothesis space, how many hypotheses should be there? So all negations, any negation means yeah, you just tell me. That's interesting. Any negation means actually it is always 0. So all are equivalent, any negation of these values. So only we'll be considering the positive values all or don't care values. I mean, only we'll be considering the literals, not, I should not say positive, literal values or don't care values. But when you use that null, which means all the hypothesis, all the consecutive CNA form using the null should be equivalent to particularly one particular fact that always it will be false. So can you tell me in that case that actually how many hypotheses would be there in this CNF form? So you have 6 dimensions, and you consider each dimension and how many possibilities are there.
Two to the power 6 minus 1, like 63. Like if you're not taking direct true for everything.
I am asking for actually the number of, I am asking for size of the hypothesis space. Size of the, yeah, of course, size of the, let me, I'm sorry, let me first ask these questions. I think that answer, you are a bit confused, and my question was also a bit confusing. So let me modify it. So what should be the number of CNFs? Yeah, I think that is also the same. What should be the number of CNFs? It's the number of hypotheses itself. Number of CNFs. So why you are saying 2 to the power 6 minus 1?
Like I'm not taking one, like true, like tautology as a CNF. Other than that, we have 6 variables, right? So a variable can be present or it cannot be present inside
what is meant by tautology here?
Like tautology means for any attribute, the output is 1.
But why should it be true for a target function?
No, I'm telling that I'm not including that.
No, but there could be also. Why are you not including that?
Okay, it can be.
So that is not fair. That is one thing. Second thing,
So for sky, it will be 4, and for others, it will be 3. We need to multiply all of them, and at the end, we need to add 1 because for that no value allowed thing.
Right. I think that is the right answer. So what should be that value? That means what he is saying that it is 4 cross 3 cross 3 cross 3 and multiply 5 threes, and only for sky it should be 4. And then there would be one hypothesis also, which is that I mean it is null because of the null value. So all are equivalent. So you may consider all null. That is also one of the hypotheses, or any null. So that is only one class, right? So what should be the possibilities in this case? Can you multiply and let me know? I hope all of you have a paper and pen with you, because I will be asking questions and now you have to answer that.
So it's 973.
973. Let us check, because those answers are there in my subsequent slides. So let me give a brief pause in the sense now it's a question answering session. So anyone has any questions on this particular part? I will take it now and then I will move forward after that. So should I continue in that case?
So why we are considering only one value for null? Like if sky is null and other values exist, like water is equal to warm.
Yeah, but
why?
your target function would be always null.
Okay, so if any of the value is null, my target function is
false. False. Target function is always false.
Okay.
So you do not require to explore. So it is not at all in that sense, admissible in that sense, that you are always considering all values are non-null, or all are null also. That is one equivalent form which represents any of them is null. Something like in that way we will be restricting our search. Which means we will be considering always there should be one form, because that is a very hard constraint. So we are assuming, though it is there in your hypothesis, there is a possibility. Okay, so let me continue in that case. Right. So so we can represent this particularly, Boolean expression or conjunction of constraints, if I say, in a form of a vector, which is instead of writing and in between, we will be writing only the literal values or the options for which this is true. Every attribute is true. Only you understand that I am not expressing any null. I can express the null conditions also there, but no, we are not focusing on that. So you see that these are the attribute sets, and these are the 6 dimensions, and which I can represent in the form of a vector. And the values, one of the examples could be like this. Say, as you see that sky, the value of sky is sunny in this hypothesis. Temperature could be, what are the, I think cool, and what are the hot, and what is the options? Do you remember? Temperature?
warm and cool.
Warm and cool.
Or both, water and temperature same. Huh? So, right. So it could be either warm or either cool. Humidity could be either high or low. Wind could be either strong or weak. No, sorry. Humidity could be either high or low. Wind has to be strong. Water should be either warm or cool, and forecast of the next day should be the same, right? So this is what is your hypothesis. If these are true, if this expression is true, then in all those days, you are predicting that all those days a person would enjoy sports. Fine, this is a hypothesis. I'm not saying no, this is the fact, but this hypothesis expresses that fact. So if it is your result from your training examples, then this is what is the hypothesis that you discover. I hope this representation is clear to you. So the thing is that X represents that particular, X is the input sample. So X is X. So what are the admissible samples here? So how many inputs are going to be accepted? Can you tell me with this hypothesis? How many input samples are going to be accepted?
8.
2 plus 2 plus 2, 8. Yes. So 8, and rest of the samples, I think we told 973 or something like that. So all those, no, that is the hypothesis space. Sorry, that is the hypothesis space. But input space is still, you understand that initially you told me that number, no? Some 96.
96.
96, right. So eight of them would be satisfied, and 88 of them would not satisfy. I hope that this is clear. You are clear that what is meant by input space and what is meant by hypothesis space. There are two spaces: hypothesis space, input space. Hypothesis space is here in this case 973 elements are there. This is one of that element. Okay, whereas the input space is 96. We'll come to those things. So X is represented as a vector and an element in the 6-dimensional space, as you can see. So this is one example, as we are mentioning. This is another example of X. Now, the first example, do you think that first example will satisfy?
Yes.
What about the second example? Second example?
Yes, it will satisfy.
No.
No,
sir.
no,
Second example will not satisfy.
change and
Where actually it is not
change.
satisfying?
For
The forecast value is not same.
Right, exactly. So this is what is the meaning of this hypothesis. So once again, those things what I just discussed with you in these previous slides. So those are the things. Once again, we are summarizing, like space of hypothesis. So H is a set of all possible hypotheses. So it's a finite number of combinations in your case, and size of input space X. I've just shown you the sets, and is the Cartesian product of all these sets, and an element in this space is a input vector, and as you have rightly said that 96 is a number, so the input size is 96. So that is what is shown. What about size of H? So I'm just giving you the explanation. So many of you have told already. So each attribute can have this many number of conditions, right? So sky is 3 plus 2 equals 4, but it seems actual size is 5120, as you are saying, but actually in our considerations we are only taking only one particular distance. So these are the so I should modify my answer to your questions. Actually the size is what you told, that is true, that is 5120, but distinct hypothesis, number of distinct hypotheses that we are going to know, we are going to learn, that we are going to learn out of this learning process is 973. So one of these possibilities will be there. I hope now it is clear to you. Is there any question?
So one small question.
Yeah.
So okay, so if like these are only like we are considering hypothesis, number of possible hypotheses, but say sky has actually 3 attributes. So for that, like we cannot form Boolean like CNF form, because
No, that's what I'm saying. That it is not the attribute value is it's forming. It is sky equals that.
yeah.
The Boolean form is sky equals.
Yeah, but in Boolean we have only 2 possibilities, like one or 0.
So that is the hypothesis expressive power, but it's a Boolean expression. It is sky equals cloudy, whether it is true or false. Sky equals sunny, whether it is true or false, or sky equals question mark, which means the expression is sky equals cloudy, or sky equals sunny, or sky equals another thing, rainy, right? So all those things, you are expressing in that way. So this is the expression, this is the representation that you need to understand.
Sir, I have another question.
Right.
Sir, in a book, in the sky, there are three options, right? So why aren't we considering two conditions true at a time? Like sky may be
Right.
cloudy or clear.
It's a very good question. Actually, we are not considering. Why? I cannot tell you. That is what we are doing. We are not considering. Yeah, it may not be correct. It may not be a good thing to do. But that is the constraint you are imposing. That is what is your inductive bias. That is what is your assumption. So the one of the motivation is that you are basically restricting your search space. You are assuming, okay, I mean, this is the only form out of which I will get a target function. It's a limitation in that sense of your technique.
Sir,
Yeah.
sir, sky equals sunny and sky equals not sunny are possibilities, right?
No, that is not considered. One of them has to be true, no?
Yeah. Sky equals sunny and sky equals not sunny are two different hypotheses.
Yeah, sky equals sunny. Actually, sky equals sunny is your literal.
Okay.
Now it has two values, either true or false.
Oh, got it, sir.
Okay. So should I continue then? Okay, so let me continue. So the concept learning, so these are the three components of a concept learning. We'll be just discussing that actually any learning task we'll have, we have already mentioned that we have task, then experience, and then performance evaluation. So the task in this case is that predicting when a person will enjoy sport. So for that, what is a more precise mathematical form that you would like to learn a target function, which is say called enjoy sport, represented by that C. And as you can see, the functional form is that there is an input space X, which is a set of all those tuples, 6-dimensional tuples, and for each tuple should be mapped to either 0 or 1. So this is your target function. And you do not know really the target function, only you know the examples. So you should adopt hypothesis H about C. So these are the assumptions as you are all discussing, that conjunctive normal form. Even there also we have little more generalized this conjunctive normal form in its expression, but restricted also on some other forms. Like those examples all of you have mentioned, that I am allowing all or by giving question mark there. That means all any conditions. I am allowing any conditions, but not any two conditions and the other is not true. So that I am not allowing for sky. So that is a kind of constraint I am imposing on my own, on my wisdom, judgment, whatever. You cannot say why always. Right? If there is an answer should be chosen from some other angle, not from this mathematical framework. Under this, so we are setting this mathematical framework, and then we will be working on under this framework to find out a function. So, sorry, form of hypothesis is conjunction of literals, and literals are in those so many forms. That means number of attributes plus two other form, that's question mark and null. So one of the example is something like this. So that was the task part, while experience is your training examples. So what are the instances are available? So possible days described by attributes: sky, temperature, humidity, wind, water, forecast. And so these training examples, when it is given to you, they are also given in the form of positive and negative examples. So that means you know their target function value. So x1 is an example of an element of the space X, capital X. And as you see, x1 is the answer is either 1 or 0. So 1 is the positive example and 0 is the negative example. And the performance measure, that means by which you can say that your hypothesis is satisfying your requirements, or what is the performance of the learning. So in this case, you will be assuming that at least your hypothesis should be true for every training samples. At least your hypothesis should be true every training samples. That is the assumptions we are considering. So which means that the hypothesis H in H such that Hx equal to Cx for all x in D. I hope you understand this kind of notations. That means you take any x, this D is only the set of training examples. D is not the whole domain. Okay, and we are considering the that in the, for those samples your hypothesis should be should satisfy the target. Your target function value should be the same as the value from the hypothesis. So in fact, as you understand, there may exist several alternative hypotheses. I have already mentioned that very trivial examples when you can represent this in the form of form of certain uh, if I say that uh, in this case, of course, as you can see that you have the conjunctive normal form, so you are not allowing any disjunction. So those possibilities are not there, but there are still several possibilities. Alternative possibilities will be there. We'll be explaining them with examples. And we have an assumption of inductive learning on H being true for unseen examples. So this is what is the basic assumption. That means any hypothesis, what is meant by this inductive learning? It means that you are extending your learned hypothesis over the whole domain. So which satisfied on the training samples, you are assuming that should satisfy also over the whole domain of input space. And the idea is that now it is basically it may not be always true that now it is satisfying all the training examples. But if we can get at least over a large number, mostly, if you find mostly they are satisfying, and hardly few cases are there where still you could not you do not find the prediction is true as the given data. Now still you assume that this should be also largely satisfying over the whole domain. So there is certain kind of concept of approximation is also there in this particular bias. Though when we are discussing about concept learning, we assume that we are exactly learning the same training function. I mean, we are assuming at least that your input samples, that means the training examples, they do not have any error. So that is the assumptions on which we will be working. So in a mathematical form, we can express this inductive learning hypothesis is that you can see that here I have used these two samples, two symbols. Let me use a pen. See, you consider this is one symbol that is a D, and this is a little stylish D. Okay. So this D represents the training examples, set of training examples. This D represents the set of training examples. Fine. And this D represents the population distribution. Okay. So these are this that means the whole domain of input. That is the whole input space. So this D is the whole input space, and this D is the training. So if you find that for all training examples, your target function is largely true, that is your target function, largely true, truly captured, rather your hypothesis is satisfying the values of target function, which I'm say approximate, this approximation part, then this is also true for the whole sample space. This is meant by your inductive learning. So any question?
So what is X here?
Oh, this X is the input sample. See, X is an element of the domain G. I should use the pen once again. See, this X is an element of D, which means X is the input set. Okay. Training example.
Training example is the subset of the population distribution.
That's right. Training example has to be subset of the population distribution. You're right.
Sir, you said largely true. So, sir, what is the formal definition of being largely true? Means largely following HXM.
Yeah. So those formal definitions require some more concepts. Like you may provide certain error bound on this particular part, right? So we'll come to those. Those concepts. So far we are assuming in this concept learning that it is always true for these training examples. But in general, when you talk about learning, and naturally the machine learning is inductive learning, as we see, that this is the hypothesis. This is assumption. I think let me stop today because we are, yeah.
Sir, please download the attendance sheet.
Okay, you are right. I will do that. Then I will also take your questions. Oh, where I can download? So then that is the question. Yeah, download attendance list. I hope it is downloaded. Right. So any question? We have 3 more minutes.
So in this inductive learning hypothesis, so what can be the output of these functions? Like, is it physical values, real numbers?
So what did you find? So far I discussed that output would be the hypothesis itself. Hypothesis itself. That is the form of the hypothesis. So this CNF form, that would be the output. A particular Boolean expression, Boolean function.
No, not that output. Like I'm asking h of x, c of x.
Yeah. So in this case, it's context dependent. So in this case, the output would be either 1 or 0.
Okay.
That is the function. So you look at the functional form. From there you find it. So you are predicting a function. So output would be that. Okay. I have to announce one thing that I have already set an assignment in the Moodle. You might have noticed that. That is, you have to submit a weekly report of your lessons, and it starts from this week onward. And you have to always submit by Sunday. That means it is not going to cross to the next week. And this report should not take more than 10 minutes, 10 to 15 minutes. Actually, it's a summary of your understanding of these lessons and also your feedback about certain some of the things which we are covering. We would also understand that, but it would be evaluated. That means you need to be true to your while reporting. It should be true to your understanding, to your state, right? Then you will get full marks. There is no issue. I have already instructed TS that if you are honest, we will give you full marks in this case. But no, if we find that it is a copy, there is not much of serious effort, then obviously there will be copy cases, there are penalties, and not serious effort means no. So you can discuss that part also. So what we want that we want that you are engaged, and if you are not engaged, let us know that also. That what is the problem, what are the issues you are facing. So it's a brief, but please submit it, and it is in the Moodle.
Sir?
Yeah.
Sir, do we need to submit in a group or individually?
No. This report is individual. See, for group, actually, we'll be setting the groups in the assignment submission itself.
Okay, sir.
So you'll find that submission by group or submission by individual, all those things will be set in the Moodle itself.
Okay, sir. Thank you.
Sir, will the slides be available?
I have already made available the first part of slide in the Moodle.
Okay.
And this one, let me go through. I mean, once I finish the topic, then only I upload it. So once this topic of concept learning will be over, then I will upload the slide. But in between, what you should do, I hope all of you have got the book. I mean, if not, please no, you have made an effort to get the book. So
Yes,
being
sir.
being at a home, being in your residence, you are limited by your, as I mentioned, this collaborative learning. That you cannot always borrow book from your peers and just go through it. It is better to have them so that you read them. So I prefer you should read always book before going through the slides. So that is also one reason why I will upload slides after my lecture. Okay, so thank you very much. So again, we'll meet next week, next Wednesday. I will set the lessons. I will set this particular meeting as usual. Thank you. Then bye.
Thank you, sir.